All right, I couldn't make it over to the lightboard, so I'm going to be doing a couple torque examples just here in GoodNotes. I'm going to start with this problem 71. So take a moment to look at this. We've got two flywheels. There's a rope connected to the smaller radii one and a rope connected to the larger one, and we're told how much force, so the tension in the rope to the right. We want to figure out how much force or how much tension to the left is needed so that the entire contraption, which is at rest, stays at rest, doesn't begin to rotate. All right, so I'm just going to highlight some of the things that we're going to need for this problem. The smaller radius is 30 centimeters. The force is 50 newtons. The larger radius, 50 centimeters. And then we're trying to find that force. So the key here is that it does not rotate. If this is at rest and does not rotate, what we need to think about is the rotational equivalent of Newton's second law, where the net torque is equal to I alpha. And if this thing is at rest and remains at rest, doesn't begin to rotate, that means the net torque has to be 0. And so we look at this problem. We've got an obvious rotation point here, this axle, and so we're going to use that as our rotation point, and we're going to calculate the torque from any of the forces in the problem about that point. Now we're looking for the net torque, so it doesn't matter what location we use to solve this problem, but using this location is going to make it the easiest to solve because we actually know the distance from here, from the rotation point to the first force and the rotation point to the second force. So this is the most obvious rotation point to choose to calculate our torques. So I'm going to sketch the forces, right? There's a force there and there's a force there. And even though it says that there's negligible mass here, if there happened to be some mass, it would be, we might draw the weight vector right there. So those are the forces that are acting on our object, and we want to then calculate the net torque. Well, we know the net torque has to be 0, so if I just symbolically write out the net torque, let's call this force 1 and force 2, well then I know if I add up torque 1 and torque 2, those have to add up to 0. Now, remember, to calculate torque, you need to take into account how far away you are from the pivot, the force that's being applied, and then the angle between the force and that radial line. And so, for torque 1, I'm just going to write out how far away I am. So that's 30 centimeters, so 0.3 meters. That's this small radius. The force that's being applied, 50 newtons. And then what's the angle between this? Well, that's 90 degrees. I could write it out, sine of 90. And the last thing I need to do is I need to think about the rotation that's going to be generated by this particular torque. And that would be rotation in this direction. So that's clockwise. So I'm going to call that negative. So negative torque. Now, the torque generated by force 2 is in the opposite direction, so that's going to be a plus sign. Now, how far away is that from the rotation point? That's my 50 centimeters, so 0.5 meters. I don't know the force. I know the angle is 90 degrees. And those have to add up to 0. So that means 0.3 meter times 50 newtons has to equal 0.5 meter times F. And so this tells me that the force that I need to apply here so that there is no rotation, this flywheel is at rest and it's going to stay at rest, that means I need 30 newtons of force to be applied. Right, so the keys here are that we identified using the rotational version of Newton's second law that the net torque equals I alpha, and in this case alpha is 0, so the net torque has to add up to 0. And then when I look at the problem, I see that there are two torque terms that I'm going to have to consider using my rotation point right at the center axis. And then I just write out the terms and solve for the unknown. All right, now let's look at a slightly more complicated example. If I can get the screen to update. So here we have a pulley, and we're given the moment of inertia of the pulley. So this pulley is rotating about that center axis. So we're given the moment of inertia. And then we're told that there are two masses hanging. We've got M2, and that's hanging at a smaller inner radius. And then we've got M1, which is hanging out here at this larger radius, R1. And we're given all of those values. So eventually we're going to plug those in. So the first thing we want to do here is we want to identify forces. We want to think about setting up this problem. And then once we do that, then we'll start to move through the problem. All right, so let me sketch out some forces. Well, I've got the string that's attached to M2 is pulling down on the pulley or the mass at this location right here. I've got the string attached to M1 pulling down over here, so I'm going to call this T2, and over here I'm going to call this not T2, T1. Right, so you can sort of think of this as an extended free body diagram because I'm drawing the forces directly on the figure. Now, there might be some weight force here if our pulley has mass, which it does, right? But we're going to choose our rotation point at this location, and so that weight force isn't going to generate a torque about our rotation point because it's directed right through the axis of rotation. So this is what I've got going on for the forces acting on the pulley. And if I wanted to draw the forces acting on my masses, I would have the weight of 2 down, and I'd have the tension in 2 up. And then I'd have the tension in 1 up and the weight of 1 down. So I've got 3 different objects here, so I've actually got 3 different free body diagrams. And in this, I might pick, this is just motion in the y direction, pick up as my positive y direction. Okay, so what we're going to do is we're going to follow some basic steps that are good to use to set up and solve these types of problems where it looks like force analysis, but you're going to also have to leverage torque analysis. So first off, for force analysis, let's just remind ourselves that the net force on any object is going to equal ma. So I've got 2 objects here, mass 1 and mass 2, that are going to accelerate translationally. So I am going to write out for mass 1 the net force. So plus tension 1, the tension is acting up, minus m1g, so the weight down, and that's got to add up to be m1 a1, right? The acceleration, the mass times the acceleration. And then for 2, I can write the same thing, but now it's tension 2 that's up, the weight down, so those are just reading directly off of the free body diagrams for my 2 objects. I just apply Newton's second law. Okay, now remember that our translational acceleration is related to the angular acceleration, and the angular acceleration is what we're ultimately going to be looking for initially, and then we'll use that information to find the translational acceleration. So recall that the translational acceleration is related to the angular acceleration when you multiply by the radius at which you're rotating. So that means we can substitute here and remember, since this is a rigid body, the angular acceleration is the same at all points on the pulley. Of course, the translational acceleration will be different because we're at two different radii. And I've left a little space here because we need to think about whether or not the acceleration, the corresponding acceleration is the same sign as the angular acceleration or the opposite sign. And so what we need to think about is, let's say that mass 1 here is accelerating in this direction. Then that would mean this mass, m2, would accelerate in the downward direction. And so if that was the case, then we would have our angular acceleration in that direction. And so that is the negative direction for angular acceleration. And so we just need to look at what we have in terms of the translational acceleration. Well, this object would be accelerating down, and that's our negative direction. And so the sign for alpha and A2 should be the same. But A1 is going to accelerate up in the positive direction, and so that should correspond to a negative sign for the A1 term when we make that substitution. All right, so now we've got our forces acting on both of the hanging masses, and we've got them set equal to, instead of ma, now ma, but for the rotational acceleration equivalent. And so now what I want to do is I want to think about the net torque on the flywheel. So the net torque about this location right here, well, I've got this force, this tension, down a distance r2 away, and I've got this tension down a distance r1 away. So if I write the net torque, well, that's got to add up to I alpha, right? That's our rotational equivalent of Newton's second law. But I've got two terms for torque that I'm going to have to add up. I've got the torque due to the tension 1, so that's going to be a distance r1 away. I've got tension 1 at an angle of 90 degrees. And then this is going to cause rotation in that direction, so that is my positive direction. And then T2, which is located a distance r1 away, a distance r2 away, T2, and that's also a sine of 90 degrees. That has to equal I alpha. And so I am going to substitute in my expressions for T1 and T2. Maybe I'll rewrite those real quick. So this is going to be T1 equals M1G minus M1 alpha R1. And this is going to be T2 equals M2G plus M2 alpha R2. And so now I'm going to substitute in. So I've got R1, and now instead of T1, I'm going to plug in M1G minus M1 alpha R1. Gonna leave out the sine 90, minus R2, and then substitute in M2G plus M2 alpha R2 equals I alpha. All right, so you can see here I've got alpha over here, alpha and alpha, so I'm going to have to distribute group terms and then move things around. So I've got m1 g r1 minus m1 alpha r1 squared minus m2 g r2 minus m2 alpha r2 squared equals I alpha. So I'm going to bring the two alpha terms to the other side. So m1 g r1 minus m2 g r2 equals I alpha plus m1 r1 squared alpha plus m2 r2 squared alpha. And so now I can factor out the alphas. So I'm going to write this as g times m1 r1 minus m2 r2. And then this equals I plus m1 r1 squared m2 r2 squared alpha. And then alpha equals g m1 r1 minus m2 r2 all over I plus m1 r1 squared plus m2 r2 squared. And so at this point, we're going to plug in all of the values that are given right here, r1, r2, m1, m2, and then our moment of inertia there, I. So we're going to plug all those in, and what we get is alpha equals, what do we get? 0.42 radian per second squared. And so that's our first answer. And then we want to go back and solve for A1 and A2. So A1 is going to be plus alpha r 1. And so that's going to be our 0.42 radian per second multiplied by the 0.5 meters. So this gives us 0.21 meter per second squared. And then A2 is going to be minus alpha R2. And that's going to be our 0.42 radian per second squared multiplied by 0.2. And so we get negative 0.084 meter per second squared. And those are our two translational accelerations. So one of the blocks is accelerating upwards, one of the blocks is accelerating downward. And that is, you know, a nice involved problem here that combines the force analysis, so Newton's second law, but also the torque analysis, and then relating the rotational acceleration and the linear acceleration. This step right here is crucial to being able to solve this problem, where you make that connection.